So welcome to this distinguished lecture series by the International Science Council and the Geo Unions. The series is part of a year-long celebration for the International Year of Basic Science for Sustainable Development. And we started this series in February of this year. Today's session will be the 5th episode. My name is Doreen Samandre-Weiss, and I'm a science officer of the Center for Science Futures, which is a new think tank of the International Science Council. Before I introduce the session itself and the speakers, I just want to remind you a bit of the housekeeping. Since it's a Zoom meeting, please keep your microphones on mute, as I mentioned. Do drop your questions and comments in the chat area on the bottom or the side of your screen. And during the question and answer session at the end, my colleagues and I will make sure to spot your questions or comments and ask you to join us through your camera if you'd like to talk to us or ask your question. So a bit about our session today. Currently, we all know that climate change is one of the main global challenges we're facing, and we've gathered enough or much evidence showing that human activity plays a big part of it. So the study of climates over the past thousands, even millions of years is called paleoclimatology. And by using different environmental evidence like tree rings, ice caps, glaciers, and coral reefs, scientists can understand what the climate was like in the past and why. By understanding abrupt changes in the past and climate in the past, we can use this to better understand climate change today and in the future and be ready for abrupt changes. One term that can also be useful for today's session is quaternary, referring to the current period we're living in and has started since 2.58 million years ago, which I'm sure we'll learn a bit more about today. Having briefly introduced this, it's my pleasure to welcome for this session Professor Maria Fernandez-Goni, who is a professor of paleoclimatology at the École Pratique des Hautes Études Paris Sciences Lettres. She works at the EPOC laboratory, which is the Environment and Paleo-Environment, Oceanic and Continents at the University of Bordeaux. So Professor Goni's expertise includes the study of pollen grains preserved in deep marine sedimentary sequences. She investigates the dynamics of climate change, glacier, interglacier, and abrupt cycles over the last million years. In particular, the interaction between vegetation, atmosphere, ocean, and ice sheets, and the impact of these changes on human evolution. She's been involved in many different international and national projects, and she is currently the president of the French Association for Quaternary Studies and the vice president of INQUA, member of the Milutin-Minkanovic Medal Committee of the European Geophysical Union. She will give us today a brief introduction on the discovery of the ice ages, astronomical theory explaining them, and the unexpected identification of abrupt climate variability, millennial to centennial in the 1980s. And I'll leave more to it later. So Professor Goni is with us online now. She has recorded her lecture to ensure that we have an optimized viewing experience for you. And then she'll join us at the end for the question and answers with you all. Please do feel free again to put any of your comments and questions in the chat and during the lecture at any time.
Good afternoon to everybody. First, I would like to tell you that I'm very pleased to be here to present my lecture entitled From the Theory of Ice Ages to IPCC Climate Projection. I also want to thank the organizer of the International Science Council for inviting me to give this talk in the framework of the International Year of Basic Science for Sustainable Development. If there is a scientific domain that has highlighted the present-day anthropogenic impact on climate, is without any doubt the research of the Quaternary era. I mean, the research devoted to the study of the recent geological past, the last 2.6 million years, when Earth was cyclically submitted to the large development of ice sheets. However, no one geologist studying since the end of the 18th century the first evidence of ice ages in the Alpine glacial, or mathematicians and astronomers studying the causes of such a dynamic of the glacial looking at the variation of the Earth position and distance in respect to the Sun, had in mind that their discoveries will be pivotal 2 centuries later to identify that our climate is passing a tipping point. Therefore, quaternary studies were contributing to sustainability 2-3 centuries ago without knowing it. Let me know first to introduce you the natural evolution of the climate system at global scale and its regional impacts. Also, how the climate is now diverting from the natural climate trend, and the issues that still remain in climate projections due to the limits in the reconstruction of past climates and the limits of models in simulating global and regional climates. The first evidence of the development of large ice sheets in the northern hemisphere was based on the observation of erratic blocks, rock striation, and coarse sediments left by the advances of glacial moraines. The compilation of all this observation by Jean-Pierre Perrodin, Jean de Charpentier, the study of the dynamics of the glacial by Ignace Venetz, and the compilation of all this information by Louis Agassiz allow Louis Agassiz to state the theory of ice ages in 1840. Moreover, the observation that in between the glacial sediment there were also organic sediment indicating interglacial condition allowed them to suggest that the Earth was submitted to the succession of glacial interglacial periods during the last 600,000 years, as you can see in the curve on the slide. The red arrows indicate the glacial periods. But what were the causes for such glacial interglacial cycles? Joseph Ademar and James Kroll proposed that 2 orbital parameters control the production of ice ages, and because these 2 orbital parameters determine the distance between the Earth and the Sun. And when you have a short distance in between, you have an interglacial, but when the distance is bigger, then the Earth enters in a glaciation. But Milankovitch added a third parameter, obliquity, that is the inclination of the Earth axis in relation to the Earth orbit around the Sun. And this third parameter, combined with eccentricity and precession, are what we call the incident solar radiation, insolation. And insolation also depends on the latitude and the season. Means that in this curve, that is the insolation at 65 degrees north and in summer, these are very important because it's at high latitudes where you can accumulate ice in winter, and you need to have a weak insolation during summer because this prevents the melting of the ice and therefore the ice accumulation and the entering in glaciation. When you compare the insolation curve with the glacial interglacial periods discovered thanks to the geomorphological data, you can see that when you have a decrease in insolation, you have glacial periods. But the Milankovitch theory, the astronomical theory of the ice ages, was challenged in the middle of the 20th century. However, some years later, in the 60s and 70s, this theory was confirmed. And in this case, it was confirmed by the study of deep sea sedimentary sequences by Cesare Emiliani and Nick Shackleton, and in particular by the measurement of the oxygen isotopic ratio of the molecule of calcium carbonate that compose the shell of foraminifera that are preserved in the marine sediment. And here you can see the pink curve is indicating changes in ice volume since the beginning of the Quaternary to the present. And what is important to note is that between the onset and 800,000 years before present, you have a cyclicity of the glacial interglacial cycles that is dominated by 41,000 cycles. From 800,000 years to the present, the cyclicity, the dominant cyclicity changed and is of 100,000 years. It is important also to note that in the most recent period, you have glacial that are much more pronounced and also that last longer. Another important contribution to the knowledge of the Quaternary climates was the study of the ice core from Antarctica. In this ice core, you can measure the delta weighting, but also the oxygen isotopic ratio, but also the delta deuterium, that is an indicator of Antarctic temperature. And you can see the black curve indicated the changes in Antarctic temperature anomalies for the last 800,000 years. And you can see that this temperature co-evolved with the changes in ice volume. But also what is very important is that in between the ice, you have air bubbles that preserve greenhouse gases. And the measurement of CO2 concentration or methane concentration allow to develop a curve in red with changes in the atmospheric CO2 concentration for the last 800,000 years. And also, you can see that this CO2 atmospheric concentration co-evolved with the Antarctic temperature and the global ice volume. And the cyclicities, the dominant cyclicity is 100,000 years. But surprisingly, in the 80s, quite recent, researcher discovered another climatic cyclicity. It was, we call the millennial scale climatic variability, and it was discovered working in the Greenland ice cores. And you can see on the right of the slide, the curve of the Greenland delta O18 is the measurement of the oxygen isotopic ratio in the molecule of the water, of the ice. And you can see that this curve fluctuates a lot, indicating changes in the temperature of Greenland. But also the studies of at high resolution of the deep sea sedimentary sequences from the North Atlantic also show that the sea surface temperature in the North Atlantic changed very rapidly, and very, very large changes in temperature. And this can be observed taking into account the variation in the percentages of the polar species. In some phases, you have almost 100% of polar species that indicate cold phases in the North Atlantic that are concomitant with cold phases in the Greenland temperature. This millennial scale climatic variability was first discovered during the last glacial cycle, I mean more or less between 100,000 years and the beginning of our present interglacial, more or less between 12 and 10,000 years. But this millennial scale variability is similar, or also can be found in older periods. Zooming in on the millennial scale climatic variability from Greenland, this millennial scale variability is called the Dansgaard-Oeschger cycles, because these researchers, Dansgaard and Oeschger, discovered this variability. And you can see two kinds of climatic cycles, Dansgaard-Oeschger cycles, one short in purple and one long in blue. These cycles have a variability between 1,000 and 2,000 years. Each cycle is composed of a Dansgaard-Oeschger warming event that is very rapid, only in 10-20 years, and has a large magnitude. The increase in temperature is between 6 and 17 degrees, and this is huge if we compare with the warming of Greenland since the 60s. This warming is more or less 2 degrees. This Dansgaard-Oeschger warming event is followed by a progressive cooling, but still warm temperature in Greenland. And the Dansgaard-Oeschger warming event plus this progressive cooling form the phase that we call the Greenland interstadial. After the Greenland interstadial, you see a pronounced cooling giving way to a cold phase that we call the Greenland stadial. The Greenland stadial sometimes are associated with major ice rafting events. Ice rafting events that are identified in the deep sea sedimentary sequences from the North Atlantic, and that they are marked by a high concentration of coarse sediment, quartz and carbonates, coming from the North American ice sheets, and associated with high percentages of polar species, indicating very cold conditions in the North Atlantic. These major ice rafting events are the result of the fragmentation of icebergs and the arrival of this of huge quantities of iceberg into the North Atlantic. These events have a cyclicity between 7,000 and 10,000 years, and they were discovered by Hartmut Heinrich, and it's for this reason that they are called Heinrich events. Heinrich events are associated with a climate phase that is called the Heinrich stadial, and can last more or less between 1,000 and 3,000 years. But this millennial scale climatic variability that was discovered in the North Atlantic and in Greenland has a global imprint. You can see here in red the Greenland temperature variation, and also in the slide they are indicated the Heinrich stadial 6, 5, 4, and 3. And in blue, you have the curve of Antarctic temperature. And you can see that in Greenland, you have a cold phase, but in Antarctica, there is a progressive warming. It means that this millennial scale climatic variability has a different response, a contrasting response in Greenland and in Antarctica. But it's a global phenomenon also because the greenhouse gas concentration co-vary, co-evolve with this Greenland and Antarctic temperature. The contrasting response to the different regions to the millennial scale climatic variability is also observed when we look at deep sea pollen record, in this case covering the last 140,000 years. From the bottom to the top, you can see a transect of deep sea core from the Atlantic Ocean. In orange at the bottom, you can see a core from the southwestern African margin, indicating the percentages of the Namakaru vegetation. In red, you have a deep sea core from the Mediterranean region, indicating changes in the Mediterranean forest. And in green, you have two deep sea core from the European margin in the temperate region. You can see that during the warm phases, or interglacial or Greenland interstadial, you see the expansion of the temperate and humid forest in Western and Central Europe. In the Mediterranean region, you can see the expansion of the Mediterranean forest, indicating both increase in temperature and precipitation. But in southwestern Africa, you see the expansion of the Namakaru, indicating more arid conditions. There really is a contrasting response between this northern and the southern hemisphere. During the cold phases, we can observe for Europe the expansion of the Central European steppe. In the Mediterranean region, the expansion of the Mediterranean steppe or semi-desert. But in Southwest Africa, you have the expansion of the Fynbos, indicating an increase in humidity, contrasting with the increase in aridity in the northern hemisphere. Now, with all this data, and in particular, in this case, with the data for the last 800,000 years of the atmospheric CO2 concentration, we can see that now we have reaching unprecedented CO2 atmospheric concentration. Now the value is 423 ppm, while during the past the values oscillated between glacial and interglacial periods between 180 and more or less 300 ppm respectively. Also, based on the reconstruction of global temperature during the Holocene, more or less the last 12,000, 10,000 years, that are represented in the black line, you can see that since 2000, this reconstruction shows a very rapid and large increase in the global temperature. But also, we see in this figure that there is another reconstruction in red that indicate a progressive cooling. This inconsistent reconstruction can be due to the fact that sometimes it's very difficult to interpret the past climatic indicators, because that we call proxies, because some proxies indicate summer temperature, other proxies indicate winter temperature, other proxies indicate changes in humidity, and still other indicate only changes in annual precipitation or temperature. But also, if we look at the simulation, we also see that the simulation are also not consistent. Some of them indicate a warming and after a cooling, and others indicate a cooling. And this inconsistency in the simulation are also observed when we project the climate for the next 100 to 300 years, as you can see on the top and on the right of the slide. There is a dispersion of climatic projection for the global temperature. Then, why these inconsistencies in the simulation and reconstruction, mainly in the simulation? Because climate is a non-linear and complex system. I mean that climate is originally foreseen by insolation, but the response of the climate, on this slide you can see the response of the ice volume, is different in comparison to the foreseen. 400,000 years ago, you see that the insolation, the increase in insolation is weak, therefore there is a weak forcing, but you reach very minimum ice volume. This why? Because between the original forcing by the three orbital parameters, by insolation, and the climate response, in this case, ice sheet response, there is in the middle a high number of internal feedback mechanisms that modulate the climatic response. And these are the Earth reservoir, such as the ice sheets, the vegetation, the ocean and atmospheric circulation, the greenhouse gases, the seasonal insolation. It means that the insolation is going to affect each of these Earth reservoirs. These Earth reservoirs are going to change, and they are going to change the other Earth reservoirs, and in fine, they are going to produce a climate response that is different in comparison to the forcing. Also, this orbital scale variability is going to be modulated by the millennial scale climatic variability. Here you can see at a point in the time that the insolation is affecting the Earth's surface, but is affecting differently depending on the latitude. In the equator, you receive the insolation perpendicularly. It means that the insolation arrives to a small surface, and therefore each point of the surface receives a lot of energy. But in the poles, this insolation is spread over a large area, and therefore each point is receiving a weak insolation. This produced a disequilibrium, a thermal disequilibrium between the low and the high latitudes that is counterbalanced by atmospheric and oceanic currents. And the most important oceanic current is the Gulf Stream in the North Atlantic. This Gulf Stream is bringing warm and moisture from the Gulf of Mexico to the northern high latitudes, and this warmth is after redistributed all over the Earth. When you have a change in insolation, you produce a climate cooling. This climate cooling, the tundra replaces the forest, the conifer forest, the taiga, and the snow over the tundra double the albedo. The albedo, that it is the amount of energy that the Earth reflects towards the atmosphere, and therefore you produce a greater cooling, and this allows the entering in glaciation. On the contrary, if there is an increase in insolation, you have a climate warming, you have an increase of atmospheric water vapor, and this produces an increase in greenhouse trapping of radiation, producing a supplementary warming of that produced by the increase in insolation. Here I'm presenting an iconic example of all these feedback mechanism of the climate system for a period that is the last entering in glaciation that occurred during the interval between 80,000 and 70,000 years before present. During this period, you have a decrease in summer insolation, and at the same time, you have an increase in ice volume. But paradoxically, the sea surface temperature in the eastern North Atlantic remained warm at long term, more or less at 18 degrees Celsius. But the air temperature in Western Europe is decreasing, is progressively decreasing at long term, as you can see, but the decrease in the temperate forest here in green. This is producing a thermal contrast between the warm sea surface temperature and the cooling in the adjacent land masses. And this is at orbital scale. But when you look at the millennial scale, you can see the same phenomenon. I mean that during a abrupt cooling in the continent, you see a warming in the sea surface temperature. And therefore, you have a supplementary thermal contrast between the sea and the land. Both orbital and millennial scale thermal contrast between the ocean and the land is producing a big amount of moisture. This moisture is transported towards the north by the storm tracks, and this humidity is feeding the ice caps. And at the same moment, as the summer insolation is decreasing, then you have the ice accumulation and entering in glaciation. To identify the role of the different feedback mechanisms that explain the observed climatic responses reconstructed by data, and also to evaluate whether these reconstructions are physically realistic, the modeling community is developing since the 70s a big amount of models. I'm going to concentrate in two types of model. One are the intermediate complexity models, or EMIC, and the other are the general circulation model. The EMIC model have a relatively low representation, spatial representation of the atmosphere and the ocean, and also of the vegetation, but can simulate thousands of years. The general circulation models have a very good spatial representation of the atmospheric and oceanic physical processes, but they can only simulate 100 years. And now I'm going to show how in fact, the mismatch between data reconstruction and model simulation. That this is important for model projections. First, I'm going to focus on the millennial scale climatic variability and the regional response to Greenland stadial and Henrik stadial. In particular, I'm going to focus on the Henrik stadial compared to the Greenland interstadials. And you can see at the top of the slide the comparison between the simulation, the spatial simulation, and the data that are represented by a star. For temperature, the model coincides with the data, even if the data are really very few. But for precipitation, there is a mismatch, a strong mismatch in the East Asian monsoon regions, because the model, that is a MIC, is modeling an increase in precipitation. But the data indicate that during the cooling phases, you have an aridification and therefore a decrease in the East Asian summer monsoon. When we look at the models, in this case, general circulation model, that simulate the warming, the rapid warming event, you can see that they simulate an increase in summer precipitation during warming event. And this contrasts with the previous model that simulated an increase in summer precipitation during the cooling event. But there is another important problem with this model, is that all the gray areas that you see on the maps, and particularly in the precipitation simulation, indicate that the responses of the model are not robust. Therefore, we need really to improve these models. With this kind of model simulation for the past, I'm showing you the East Asian monsoon projection for the future. and for 3 scenarios. One at 1.5 degrees of warming, the second one is at 2 degrees of warming, and the third one at the bottom of the slide is the 4 degrees Celsius warming. And you can see that this model, that is a general circulation model, indicate that there is with the warming, there is an increase in winter rainfalls, while the summer precipitation does not change. This is a seasonal paradox proposed by the numerical simulation for the end of the century, because during the past we know that is during the warming event when summer precipitation increased. Therefore, this paradox strongly questions on the reliability of the numerical simulation and the drivers controlling the regional and seasonal precipitation patterns in East Asia. Now I'm going to take an example for the Holocene, our present interglacial. And this figure, the black line, represents the Holocene global temperature evolution. And this black line is the result of data. And you can see that there is a thermal optimum at 6,000 years before present. The blue curve and the gray curve are simulation. And you can see also that they cannot reproduce this thermal optimum at 6,000 years before present. But when the modelers add the southern Greenland vegetation in light green, the southern Greenland vegetation plus the Arctic vegetation in green, and the southern Greenland vegetation, mid-latitude vegetation, and Arctic vegetation, with the sum of these vegetations, the model reproduces the thermal optimum of the Holocene. And this is why? It is because this increase in vegetation is decreasing the albedo. And when you decrease the albedo, you are decreasing the amount of energy that the Earth reflects towards the atmosphere, and you are producing an additional warming to that produced by the original increase in insolation. Then you see the importance of the different processes, and in particular of vegetation changes in reproducing the data, the observation. Here is another example of mismatch, but in this case it's a multimodal approach. This multimodal approach is trying to reproduce the African monsoon, and as you can see on the slide, is what the modelers call the African nightmare. These models, all of the models are trying to reproduce the African monsoon at 6,000 years before present. And you can see that there is a lot of dispersion depending on the model. The results are not very consistent, are more consistent between 8 degree north and 16 degree north, but still this model underestimates the northward shift of the African monsoon that reach more or less 17, 18 degrees north. But when the modelers add interactive vegetation, the African monsoon is better represented. And this is this model deficiencies is due that the atmospheric physics are still not very well constrained, and also the coupling with land surface, such as vegetation and soils. Also, the balance between different effects is still unclear. Now we are still in the Holocene, and as we know that the interglacial in the past lasted between 10,000 years and 30,000 years. And we know that our present interglacial started more or less 10,000, 12,000 years before present. Therefore, we can wonder whether we are going to enter in glaciation. If the Earth is entering in glaciation first, and when, the timing of this glacial inception. To tackle this question, Ganopolsky et al. Have developed a EMIC model, and they have found a relationship between the atmospheric CO2 concentration and the boreal summer insolation. And this relationship is reproducing well the entering in glaciation for the past 800,000 years. And this author have applied this relationship to the future, and they have found that the timing for the next glacial inception will be in 50,000 years from now. In fact, now we are in a moment in which the insolation is decreasing, and maybe we should have been entering in glaciation before, but with the big increase in CO2 concentration, the Earth skip to this glaciation, and the glaciation only would occur in 50,000 years. However, this EMIC model, as I told you before, has a low resolution atmosphere and ocean representation. The ice sheet module, Psychopolis, only takes into account the northern hemisphere ice sheets, and also the vegetation module is very simple. Then the need for improving this model for knowing the next entering in glaciation. Finally, another example of multimodal approach concerns the evolution of the global mean sea level from 1950 to 2100. And there are several models that are projecting the increase in global sea level, and most of the models indicate an increase of 1 meter. This model takes into account the ocean thermal expansion and the melting of the glacial. But the only model that is more realistic in a physical point of view, because it includes ice sheet instability processes, project an increase in the global mean sea level change at about 2 meters. The IPCC report indicates that this model is the low likelihood, but in fact is the more realistic in a physically point of view. Maybe this model should be the high likelihood, unfortunately. In conclusion of this presentation, I'm highlighting the uncertainties in data reconstruction and model simulation, the inconsistent climate responses from different models, and the mismatch between simulated and reconstructed past climates. And these highlight the difficulty in modeling regional and global responses to past climate changes, the necessity to improve data coverage, methodologies, and uncertainties. And for instance, you can see a very recent database and you can see that the Southern Hemisphere data are underrepresented in comparison with the Northern Hemisphere data. Then we need more data from the Southern Hemisphere in particular. And also there is a need to improve models by using more systematically paleoclimatic information for model tuning and model development. All these issues have a strong implication for future climate modeling, such as the projection of sea level rise, the timing of glacial inception, and the regional impact of global climate change. But more generally, we have to say that the basic research on the Quaternary is still needed and requires a long-term perspective if we want really to understand the climate system and improve climate projections. And as we are in the Quaternary, studies on the Quaternary provide more than that, because they are crucial to identify the biological and cultural mechanism behind human evolution since the emergence of our genus Homo circa 2 million years ago, I mean at the beginning of the Quaternary. I would like to end my presentation by warmly acknowledge my colleagues, Pascal Braconneau, Didier Paillard, Thomas Extier, and Coralie Zorzi, who helped me through several discussions to create this presentation and improve it. Thank you very much. And now I'm open to any question.
Wonderful presentation by Maria. It was really there was something very deep to see all this presentation and see how climate has changed over the past, thousands and millions of years, and how this is helping us understand better how these different, very complicated processes on the planet have impacts on each other, and we're still trying to understand them. There was something that jumped in for me, which was particularly comparing Greenland and Antarctica, and how the effects at the very end are not exactly, maybe it was generally the same, and then towards the end, actually, we saw that Antarctica is not actually the same as Greenland. Yeah, I was wondering also, maybe I can ask the first question on the model for the sea level, because you were saying it was the most realistic or high probability model. I was wondering if you can elaborate a bit on this, because this is what the IPCC also mentioned, and what other models or what you believe is used for sea level specifically.
This is a very difficult question for me, because I'm not a modeler, but the fact that there is only one model, but the most realistic, saying that the sea level rise will reach almost 2 meters, I think is, even if it's only one model, is the more realistic. Then, this is the question, I don't know why is a low likelihood, I don't know, because this is only because it's only one compared to 3-4 models.
Yeah, so the range is not very clear even.
Yeah, no.
We have a question from Alec. Please go ahead, Alec.
Thank you very much, Doreen. First of all, Maria, I thank you sincerely for the wonderful lecture, which clearly show us how theory, models, and data, meaning the basic science, help us in solving the problems, urgent problems of society, which one of them is the climate change, and it's exactly fit the climate action sustainable development goal. The point is, when I mention particularly the model and data, they are both the essential components in the studies of the climate and its variability. However, both components are polluted by errors and a lot of uncertainties inside, and sometimes they interplay. I will explain what I mean, actually. First of all, just to mention to those who don't know some particularities of the model error, that they comes from many sources which is uncertainties in paleo data, uncertainties in the methods, discretization errors, etc., etc. But you, Maria, clearly showed for example, in one of the examples, that the circulation model fails to fit the mean temperature during the Holocene time. And I remember the peak 6,000 years, and the model failed. But when the vegetables are added, the model fitted rather well. My question now comes, how robust is the assumption that if we add vegetables, which paleo vegetable data actually, correct? Yeah, and this really improves model. Because if you look at the model for 1,000 years, model perfectly, I could say, as a person dealing with models, fit data and the model results, but not they diverge after the 1,000 years, and the data don't fit the model. My question is, how could this assumption, meaning that this is the only things, but might be the problem is that the paleo data are polluted, paleo data are uncertain, or maybe I'm wrong, and this is something which can be very well determined. That's actually a question, interplay between different errors, yes.
In this case, first, the model that they use, there was no vegetation at all. And this is not true, because we know that during the Holocene, and in particular, more or less at 6,000 years before present, a large part of the northern hemisphere are really dominated by forests. Then even if you have a very rough kind of vegetation that is only forest, without distinguish between Mediterranean forest, temperate forest, and so on, but a very coarse idea of the vegetation biomes, that is forest, when you add that, really you improve, the simulation. But the problem, there's another problem, is that this presentation, this vegetation, in fact, is only is static. I mean, when the modelers, I think, if I remember well, when modelers add this vegetation, the vegetation is not changing due to the changes in insolation, for instance. Therefore, in this case, the model is not completely well, is not running completely well, cannot simulate completely well the temperature, because vegetation is not changing at the same time as insolation changes. And this is a source of error. It's not uncertainties, but it is a source of incomplete simulation.
Yeah, thank you very much. Yeah, because it was very short, but I just looked at this, that there is a part of the model which fits very well data, but the part of the model which, when we're going to the time for this becomes, it's really diverse. Yeah.
But maybe is this because vegetation is not is not a dynamic vegetation, changing with changes in insolation. They only put at 6,000 a lot of forest.
I see.
This is one of the problems.
Thank you.
Thank you, Maria. Maybe I can ask another question to see if we have more questions coming. So you, at the end, you were saying we need to improve the data that we have, we need to improve the models, and more specifically, you were mentioning that we need more data from the South, the global South. And is there a particular space that we need to know about from the global South, or is it really most of the things that you were mentioning in the presentation? Could you elaborate a bit more on that, on what we know from the global South and maybe what we're still missing?
for instance, we have very few data about the millennial scale climatic variability in the tropics, and in the tropics, and also in the southern hemisphere, in South America, in Australia, in Africa. There are very, very few data about the millennial scale climatic variability. In particular, also in the continent.
Yeah, and indeed, it's what you were saying, that because all these different effects are, that's what we need to understand, to be able to understand the interactions, to be able to improve the data and the models. It's a global effort.
Yeah, exactly, because these data are indicating also regional climates, and regional climates also affect the global climate.
Yeah.
As I show you for the last Tentherinic glaciation, is something that we see that there is a question of regional climates between the continent and the ocean, in the Western European margin, and this is affecting the global climate because it's affecting the globalized accumulation.
Yeah, yes, indeed. And I think everyone is so happy with the talk, and they're really congratulating you on the clear presentation. They're already asking for the recording to be available. And there's also this comment from Laurent Strauss that I will just mention to you, saying that he hopes that the politicians, mainly those in the thrall of the petrochemical industry, don't continue to use the uncertainty of the predictive models to do little or nothing to change the trajectory of global warming as we race toward disaster. So I don't know if you have a comment after that, but I wanted to share it with you.
Thank you.
And then there's a question from Hartmut Heinrich. Please go ahead, Hartmut.
Maria.
Hi, Hartmut.
Very nice comprehensive talk. I like your conclusions relative to the ice sheet instabilities. And I see that a lot of physics is not known, and especially in the Antarctic, the regional situation is very complex. What I see in the modern literature is that it seems that there is a heavy attack of the warming ocean on the glaciers. And my personal fear is that anthropogenic warming is a kind of experiment to trigger a Heinrich event, and which would be really terrible. Do you know how much, it's not only sea level rise, but a lot of fresh water is introduced from the Antarctic, which could close the door from the Indian Ocean to the Atlantic. That means cold water gets into the conveyor belt, which could cool a little bit. Do you know how much this is included in models?
You know, Hartmut, I'm not really a modeler, and I cannot answer this question really, because I'm not a specialist of the Southern Hemisphere, and I'm not a modeler. But as far as I know, no, I cannot answer. There are a lot of processes that are not taken into account in the models, or are badly taken into account. Because, for instance, for EMIC, the representation of the winds, for instance, is quite limited. Or the oceanic moisture production also is not really well taken into account. But really, and also I'm referring almost to the northern hemisphere, to the North Atlantic or the North Pacific. But for the Southern Hemisphere, I don't know, Hartmut. I'm afraid.
So you have the same status as I have. But you mentioned the wind. You have a nice picture in your presentation on the sediment of a Heinrich event in the Northeast Atlantic. And what thrills me is that so much quartz grains in these events, up to 80% in the Northeast Atlantic. And my impression is that this is wind transport. And unfortunately, nobody is interested in wind transport, either from North America or from Europe, from the European ice shields. So I have no mechanism in my mind which could produce such a sorting, 80% quartz grains and less than 20% ice rafted debris.
Okay, but I thought, in fact, that really that the wind cannot transport this ice raft debris, because at least the big ones.
Yes, that's right. What I have in mind is we have a lot of sediment transport across the tropical Atlantic to Brazil and the Caribbean.
Okay.
And we know that the sediment which is transported most are quartz grains because of their electrophysical behavior. And when you have a strong winds in the Northern Hemisphere, which could take up sediments from the moraines, and you have a wide transport of sediment, then it could be possible that you have a strong influence of wind transport.
Of course, but in a fraction that is finer, no, than 250 microns.
No, 250 micron not, but
yeah, but finer than that.
Right, smaller one. But nobody's interested in research.
No, I understand very well. Yeah. You are right. Yeah, it's true. Yeah.
Okay, good luck. Thank you very much.
Thank you, Herman.
Thank you. So far, I think we got the questions that we wanted to ask in the session, and actually we're already ahead of time. Not ahead of time, behind time. Maria, if you just want to say the last maybe wish that you would like as a paleoclimatologist to leave us on that note for the session.
I think my last thought or the take-home message is that we need basic science, and in particular, in quaternary is really important, to understand the climate system, because you have the condition that are natural without any anthropogenic impact. You have the baseline condition of the climate, of the natural climate, but we need a long-term perspective. Mm-hmm. We need a long-term perspective, and sometimes, in fact, all politicians and so on are only thinking at very short term.
Yeah.
And also, I think this is a problem for basic research, because they want a solution, a quick solution. But the quick solution sometimes is not possible, a quick solution.
Yeah, and especially not to something as big as climate change. It has to be much further. Yeah.
Yeah. And also, yeah. Mm-hmm.
Well, definitely, I think your session, your lecture has put such a good impact on everyone. So many people have congratulated you on the clarity of your presentation. So thank you so much. I think you'll leave lots of people thinking about how to tackle the situation and what we're thinking about in paleoclimatology and the models that we have and what we can do for the future, or think about for the future. So thank you so much, Professor Maria. This has been a great presentation, and thank you all for being here.
Thank you very much to everybody who had time to listen the talk, and I'm very happy that you distribute, the recorded presentation.